Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Invisible queue. Thanks everybody for coming for the sixth and final series ender of crypto with senior cryptographer Josh Binelow from Microsoft Research. Raise your hand if you've been to every one of these in person. Okay, cool, awesome, good, thank you. And in the back, is that Sandy in the back?
Yes.
Okay, cool. So what we're gonna do, just to give you a sneak at it, is I'm gonna give you guys some lockpick sets. Not like the cheap ones though, like the pretty good ones. Not over like the area where you have to sign off the tax thing, but as close as I can get. So it'll be a little bit of time to order those and get those shipped to you. I'll interoffice mail those to you as well as probably email you since I have all your aliases. For everybody involved, both who's been to any of the sessions, we're going to send out a questionnaire. I appreciate your feedback on that so that Josh and his counterparts and people in security can do more of these more often as they're relevant. So without further ado, one more round of applause for Mr. Josh for all the contributions he's been doing for cryptography. Thank you, Josh.
Thank you, Justin, and welcome survivors. Sixth and final. All right, so let's get going and get into sort of some of the interesting what you can do with this. Just as a reminder, if anybody missed the last session, we talked about attacks of various kinds, vulnerabilities, attacks, especially side channel attacks, but lots of related things that can be done. And we talked about some of the practical considerations that often give rise to these attacks, how you can do a lot of the things that we need to do in cryptography as efficiently as possible. So this time, we're going to move on to some of the tools, the higher level things that can be done with crypto. Homomorphic encryption, specifically. A few people asked me about bilinear maps and pairings, so I'm going to spend like 2 minutes just squeezing that in, but I'm not going to do much there, just to give people a quick sense. Secret sharing, zero knowledge, and give a few applications to these. The applications in particular, computing on encrypted data is becoming a very hot field in a lot of ways, if you think about it, for very obvious reasons. If all your data is in the cloud and it's encrypted, what do you do with it? It's just basically, do you use the cloud as just a big storehouse and can't do anything? Or if you can actually encrypt on the data in the cloud, you can do a lot more. If you can compute on the encrypted data in the cloud, you can do a lot more with it. The other thing I've been promising, I'm going to talk a little bit about elections. It's a good motivating example and one near and dear to my heart. So I'll spend a little bit of time on that. So let me start on the computing on encrypted data application. And in particular, if you want to work on data, do something with the data in encrypted form, let's remember what symmetric encryption typically looks like. Something of this sort, where you've got sort of an ugly function in here, and you're just taking this data and making a mess of it, right? You're trying to remove all structure, you're getting something that looks nothing like the original or anything else. It's really hard to do anything with data that's been actively messed up as much as possible. However, when we look at what we do for asymmetric encryption, we've got nice equations, right? We've got things like this for RSA, where there's a nice mathematical description of the relationship between the plain text and the ciphertext that we may be able to work with. Is that a question? So in particular, RSA excuse me, is multiplicative. And we mentioned this early on, a couple months ago, I think. Basically, if you take an RSA encryption of one message and an RSA encryption of a second message, and you literally just multiply these two together, multiply them mod n, because everything is going on mod n here. Literally multiply them. What you get, if you work it through, is a completely valid encryption of the product of the two messages. Now, normally we put in all sorts of padding to prevent this from happening accidentally, but sometimes we want to be able to do this. We want to be able to take the data and operate on it. And here, if we take this as raw RSA, take this data, take these two messages, in encrypted form, we can multiply them together and get a useful bit of information and a representation of a computation. This computation in particular, multiplication. So RSA isn't the only example. There are a bunch of functions like this. RSA in particular has this multiplicative homomorphic property. Another very common function is the El-Gamal cipher. El-Gamal is really just, you do the Diffie-Hellman key exchange, and you use that key as a one-time pad, effectively. You use that key and take the key and multiply it by your message. So here's the message here being multiplied by what would come out of the Diffie-Hellman result. And the recipient on the other end can sort of work this out and remove the key and just get the message. And if you work this through, there's a pair of values, but if you multiply things appropriately, again, you get a multiplicatively homomorphic function, also very commonly used. Now, there are some others. Goldwasser-Macaulay came up with this function that looks like this. It's designed for encrypting just a single bit, but it has some nice mathematical properties, some provability. So it was a really interesting function when it came out. And it has the property that if you multiply two Goldwasser-Macaulay encryptions, you get an XOR of the bits. Okay, can be useful for something. Years ago, too many years, literally 25 years ago, I generalized this. It is 25 years. So here's another function, just a straightforward generalization of that, but what you get is something that's additively homomorphic. If you multiply two encryptions in this form, the trick is the message is in the exponent here. So with the message in the exponent, if you multiply two things, g to the m1 times g to the m2 becomes g to the m1 plus m2. You get an additive function. This had some nice properties. One not so nice property was decryption is kind of cumbersome with this. It's possible, but it's kind of cumbersome. Some applications, that's OK. Some applications, you want to be able to decrypt. So Pascal Payet came out about a dozen years later with a generalization of this, working mod n squared, so you get some blow up in the ciphertext size, but it has the advantage that decryption is much more straightforward and easier to do, also additively homomorphic. So these are the most commonly used homomorphic functions, but you can develop others. There's a whole host to choose from. So we have these things that we can do. We can do additive, we can do multiplicative. What we'd really like is something that does both. That was the holy grail for decades. If we could simultaneously add data that's in an encrypted form and multiply data that's in an encrypted form, you can provably do everything. You can build out any function you want from just those two operations. And it was long thought that would be great, but it's not possible. Nobody was able to prove it, but it was thought this structurally is just asking too much. Until 5 years ago, Craig Gentry at IBM found a way to do this. Now, a way to do this kind of in theory. I write it as wildly inefficient. If you have another adjective that you could put there that's more superlative, put it there. Wildly in this case is about 25 orders of magnitude slower. 10 to the 25th power, think, modern processor does a couple billion instructions per second. Well, this is a couple billion years to do one instruction at this pace. Yes, it's possible in theory, really interesting, but not quite practical for cloud computation. But since then, there's been more work done, and things have gotten a lot better. It's still very inefficient. We've shaved off a dozen or so orders of magnitude. It's still about 1 trillion times slower than not working on encrypted data. But now you can do a cycle every maybe 5 minutes or so, 10 minutes, something like that. We're getting there. What's more interesting right now, we'd love to get this general form done. People are working hard. There are a lot of people working on this. But what's more interesting right now is many special cases really are practical. You can't do a full general computation of all sorts, but you can do a lot of specifics. And I'll quickly mention one way of building an interesting specific, and that comes from bilinear maps. Yep?
What's the status of homomorphic encryption that's resilient against quantum? So I'm just curious, so since you can give a one-line summary of that.
Oh, well, so let me roll that back a step and ask what's the status of encryption that's resistant to quantum attacks? And pretty much all of the public key stuff that I talked about is potentially vulnerable. If you built a good quantum computer, you could factor. That breaks RSA. You could compute discrete logs. That breaks Diffie-Hellman. Some of the lattice-based things that I talked about, the elliptic curve-based stuff also is based on discrete logs. Some of the lattice stuff seems like it may be resistant, so we might want to move that way. I talked about lattice things, I don't know, a month and a half ago, something like that. Those can resist. The ones that I showed just now, all these homomorphic ones, are based on these mathematical properties that would fall if we were able to build a good, efficient quantum computer. However, the best quantum computers right now can factor 15. That's what we're up to. There's some promising ideas, but there are also some fundamental barriers. And it's really not clear whether or not it's even possible. It might not be a technological limit. It might be a limit of physics. We really don't know. But there are some promising directions that people are going. And there is active work going on to talk about post-quantum cryptography. What do we need to do to be ready just in case? And there's a lot of work in that area. OK, so let me spend a couple minutes digressing to talk about bilinear maps, or pairings, people like to talk sometimes. There are people in the room who know a lot more about this than I do, but I'm going to give you a quick sense just to give you what we can do. And the idea is you have two groups. We talked about mathematical groups when we talked about elliptic curves. Two mathematical groups and two elements, presumably generated. And you have a function that takes elements of one group to another group with this property. Now, actually, excuse me, these two things could actually be separate groups. This could be G1 and G2, but let's not complicate it. Let's think of the simpler case of a pair of things from the same group going into this other group. And it has this property that if you take G to the A and G to the B, you get the corresponding H to the AB in the other group. Now, this little explanation, Ron Ravesh showed it to me about a month ago as a good way to try to explain it. And I think it's a good way to just get a little bit of a sense of what's going on. So first, an important thing to note is that you have, if you compose with G to the power 1, you get H to the A. So you can go from G to the A to H to the A if you have one of these functions very easily. So if I take a bunch of these objects, any of these, I can go to the corresponding object in the G group to the corresponding object in the H group. And the reason I'm listing these objects is this is the Diffie-Hellman problem that we started way out on early on. If you have G and G to the A and G to the B, nobody knows a good way to get to G to the AB from that. But if you have A or B, if you generated one of these two, then you can get this. This was the Diffie-Hellman key exchange. But nobody knows how to go from these three to this one, or these three to this one. But we can construct groups with bilinear maps such that you can go from this pair to this in this other group. Okay? I'm not going to go into any detail about how or why, but you can actually leverage this to do lots of interesting things. One thing in particular is you can build a homomorphic encryption function where you can do as many additions as you want, and you get one multiplication, kind of for free. So now here's a slightly more complicated function that you can do. If you can do most things in addition and you need to do one multiplication, we can do that. And you can go from there. Small numbers of multiplications now we can handle reasonably well. Fully general computation, not so good. But many special cases we can handle. OK, so I'm going to go back and look at one of the simple ones for a minute and try to motivate this application that I'm going to talk more about later. So suppose we have just a simple additively homomorphic encryption function, the kind we had 25 years ago. Call it 8. And I want to encrypt votes as one. Encryption of 1 is a yes vote. Encryption of 0 is a no vote. All I have to do now is homomorphically sum the votes, and I get an encryption of the sum. So if you think of this, if you want to vote yes, you encrypt 1. If you want to vote no, you encrypt 0. And we post all these encryptions. Anybody can see them. And all I have to do is take them, literally just multiply them together, decrypt, and you get the tally. OK? That's the basic idea. Now, there's a lot that's missing here. First of all, who holds the decryption key to do this? Right? If I hold the decryption key and can decrypt in the end, I can also decrypt all the intermediate votes and see how everybody voted. Probably not such a good thing. Who's actually doing the encryption? Right? If the voters encrypt, then the voters have to have some devices that'll do encryption. If they use their own devices, there are these little malware type issues that might get in the way. There's also coercion kinds of stuff, because somebody could give you their device to use and say you vote on this device, or install something that captures your vote. And there are some problems there. How do we ensure that only 0s and 1s are encrypted? Right? Maybe I really want to vote yes, so I'll encrypt 1,000,000. Put that up there. And that gets summed up with all the zeros. And sorry, nobody else voted anything but 0, but I voted 1,000,000. We win. So we have a few issues. And I'll get to these later.
If all of the encrypted values are either a 1 or a 0, then there are only 2 encrypted values, right?
Not if you use a randomized encryption. So yes, you're absolutely right. If we use a deterministic thing like straight RSA,
Is there anything in the randomized encryption that is compatible with the homomorphic?
Yes, absolutely.
manipulation?
Okay, so let me.
That doesn't make sense to me.
Let me go back a little bit. Come on, back. So this function I developed specifically for use in elections. That was my motivation. That was my dissertation. So effectively, what you can think of as M is the vote here, 0 or 1. R is a random value. And it turns out if you multiply 2 of these things, you get some other random value to this power e times g to the sum. And because of the way things are structured, these random things to the power e can be pulled off at the end. But there are many ways of encrypting the same message by just having different random values here. So that can do it. And El-Gamal has the same property here for multiplicative. You have a random value that's part of this. It's just RSA that's completely deterministic in its raw
keep
form.
all the random values that were used?
You can keep all the values. Another way, remember when I said decryption is cumbersome? It would be a matter of figuring out what the random value, what the aggregate random value would be. You can, if you do that, then decryption is easy. But if you don't keep that, then it's more work to figure out what the aggregate R would be. But you can find out. With this, there's actually an easy way to strip away this R to the n if you know the factorization of n. Regardless, you don't have to keep track of what R generated it. OK, forward. There we go. OK, so the next thing I want to talk about is a very valuable tool called secret sharing. Has lots of applications, and it comes out of a basic mathematical fact that if you take any k points in the plane, as long as they have distinct x values, then you can interpolate a polynomial through them of degree at most k minus 1. OK? So why do we care about this? Well, I'm going to show you the simplest case, the easiest to remember. 2 points describe a line, right? You have 2 points, you can figure out the line that goes between them. So what I'm going to do is start off with point in the plane, and I'm going to take a secret. And my secret value is going to be over here. My secret value is going to be 0 in the x position and some y value, and I'm not going to tell you what this y value is. That's my secret. And now I'm going to draw a random line that goes through there. And I'm going to give everybody in the room, or everybody I want to share this with, points along this line. Okay? Now, if later on any two people come together, they can figure out what the line is, they can figure out where it hits the y-axis, they can find that point. But if there's just one person, then that point could be anywhere, right? You don't know. It could be anything. You can draw a line through those 2 points no matter where on the y-axis the secret is. So they're all completely consistent. You literally have 0 information at all. Even though you've got, in some sense, half of what you need, you've got one of 2 shares, but you've really got nothing. Okay? So this generalizes beyond lines to arbitrary polynomials. So let's say this looks vaguely like a degree 4 polynomial, maybe. So maybe I gave out points on this degree 4 polynomial. So any 5 of these points is enough to figure out what the whole polynomial is, and therefore figure out what the secret is. But if you have only 4 of these points, then you really have nothing, because any 4 of these points is consistent with any possible value here as a 5th point to give you a degree 4 polynomial. So there's a very sharp threshold in one of these things going from 0 information to complete information. Okay? Once you have this way of sharing information such that you can build this sharp threshold, you can build a lot of tools out of it. So the simple way to work with this is just generate random polynomials. Here's your secret. You have n people you want to share with. Any k can reconstruct. And you want to make sure that no fewer than k get any information whatsoever. Instead of thinking of it as building the polynomial and points on a polynomial, all you have to do is pick random coefficients, make s be your constant term, because p at 0 is going to be s. And then these are random values, and you just give out this at random points, or even consecutive points. P1 through n is fine. Very simple to do, very efficient. Turns out to be also very efficient to reconstruct. There are some very simple interpolation methods. And you can do this geometrically over reals or rationals. But this also works if you're doing all the computations mod p. So now we get back into the computer science domain, where picking a random rational number is not an easy thing to do. But picking a random or a set of random values here in the range 0 to p, or 0 to p minus 1. That we know how to do. All those possibilities now are equally likely, and all the possible secrets in the range 0 to p minus 1 are equally likely until you reach the threshold of information. Okay? So this works for distributing a secret. You can actually do some interesting computations on shares. It turns out, maybe I should have put in a slide for this, but if I give you shares to secret A, and somebody else gives you shares to secret B, you can take your share to A and share to B and add them, and you've got a share to A plus B. If you work it out, basically, polynomials in some sense are linear, at least in that sense. As operators, they are. You get a share of just the sum of the coefficients, and everything works out. Right. Oh, wait a minute. Now, the share of the coefficients, that's not right. But the points just add up. Everything works out well. Also, if you multiply, the same thing happens. You get a share of the product. But the problem is that now the degree of the polynomials grows. So it takes more shares to reconstruct the polynomial and get the secret. So it works really well for addition. If you're going to do it for multiplication, you have to be able to deal with more shares, maybe correct and reshare things, and there are some tricks for that. Using techniques like this and similar techniques, you can develop threshold encryption. Threshold encryption is a way of encrypting such that you have n shareholders of the key. If any k of them are willing to cooperate. They don't have to actually give their share, their key up, or their whatever piece of the key, and reconstruct the key. They can each perform some function on the ciphertext, and after the last one has performed it, or after they put together their pieces of the decryptions, then you've decrypted the ciphertext. Okay? This has the application in elections that we were talking about before, right? You don't want one person to be able to decrypt all the votes. You normally have a board of elections that adjudicates disputes or whatnot. Maybe there are 5 people on the board. Maybe it takes a majority to resolve things. So you do a 3 out of 5 threshold encryption scheme on all the votes. And now any 3 of the members can get together and decrypt the sum. But it also takes 3 of them to collude to figure out how anybody voted. Or maybe you want it to be 4 out of 5. You probably don't want it to be 5 out of 5, because then if somebody doesn't like the way things are going, refuses to decrypt, or loses a key or whatnot, you kind of lose the election, which is not a good property. So this threshold thing allows you to have some robustness and still have some protection, so no 1 or 2 or whatever threshold you set, people can figure out how people voted. Okay. You also can build group signature schemes. Group signatures are sort of what you might think of when you are signing something important. Maybe a bank is signing something, or something where there are corporate requirements, and you want this is a check for $100,000, so it takes 3 officers to sign off on it, out of the company's 6 officers, say. But you can do it in such a way that you can check, yes, this has been signed by a sufficient number of people, but the person receiving the signature has no idea which of the legitimate people. So some 3 of this group of 6 did sign it, and that's all I need, but I don't know which 3. And you can even generalize this in ways so that it can be the president of the bank and 1 vice president, or 3 vice presidents on their own, or 2 vice presidents and 3 tellers, or whatever it is. You can generalize it in forms such that some people have more power than others in this. But you still, all you get is, yes, this has met the requirements to be a valid signature. I don't know exactly which set of people signed it. Okay? Again, you can see useful applications there. All right. One other tool I want to spend some time talking about. You may have heard of this sort of bizarrely named thing called zero knowledge. And let me give you a little bit of a sense for what it is. But any questions before I go on to this? Because it's going to take a few minutes. OK. So zero knowledge really comes out to believing something without seeing it. Seeing is believing. Well, let's do it the other way. And if we were in a small group, if there were, I've done this, if there are half dozen people, I'll do this with actual cards. But I have to simulate this here. So it will be a little less convincing, but you'll get the idea. What I want to claim is that all of these cards that you imagine I've dealt out are red. Okay? And what I think I could do is show them to you. See, they're all red, but no. I want to convince you that they are red, or at least that a card is red without your seeing it. So what I'll do is deal out these cards and have you pick a card. Now, if PowerPoint were really nice and dynamic, I could, you pick a card and I flip that card, but I have to simulate this. So you just picked card 2, right? And I turned it over and show it's a king, and particularly a red king. And then you pick card, let's say 5. And I turn that over, and you pick card 3, and I turn that over, and you pick card 1, and I turn that over, and phew, I remember the sequence right. I've done this before where I've gotten it wrong, and it's embarrassing. OK. So what do you have at this point? When you get through this, I've answered all of your challenges correctly. I've shown you that these cards really are all red. So this last card, now, you've never seen this card, or the underside of this card, but still, you have pretty good reason to believe that it's red. You're not a 100% sure, but this cut and choose thing kind of worked, and you're pretty convinced that it's red. And in particular, this is an interesting kind of belief because it's non-transferable. If somebody else walks into the room and say, yeah, I'm sure that card is red, and that person just walked in and said, okay, convince me that it's red. Well, I can't. I know that it's red, or I have reason to believe it's red, but I have no way of convincing you that it's red. Mm-hmm.
Is the essence of why I lit it and the next person doesn't lit it the fact that I had the choice of which ones to sample?
Yes, you participated in this proof. So if there's somebody who was there the whole time but thinks you might be colluding with me, say, then they have no reason to believe it either. But either way, if you are isolated from others at the time, and it's you're making the choices, then you can't transfer this. If you're there as sort of a wire, somebody is whispering to you choices to make, then that person will be convinced and maybe you won't.
Is there a way that we can share some secret?
There is. It becomes cumbersome. There are a few things. There's actually a more general approach to this of using the choices themselves to generate the randomness. It's called the Fiat-Shamir heuristic, and I'm not going to say anything more about it unless you're interested, but it's a really clever way of handling this and making one of these zero-knowledge proofs non-interactive so that anybody could just look at the proof after and be convinced of it. But
is the non-transferability a feature or an anti-feature?
It is usually a feature. Sometimes it's an anti-feature. Think of it in the election context. It's a feature of your being convinced that this is your vote without your being able to show it to somebody else even if you want to. But there are contexts where it's not a feature. So let me show you what this looks like. Of course, in the crypto the scenario, in that context, there are no cards, there are encryptions. But it's basically the same thing. I show you a bunch of encryptions. I claim these are all encryptions of the string red, and you pick one. Let's shortcut it. You pick the one to stay. I'll reveal the others. Now, the way to open these other things, I'm decommitting in some way. So one thing I could do is, if these are encrypted, I show you the randomness that was used so that you could check yourself. If this is a public key encryption, you can repeat it. There are other ways of opening up commitments. You think of one-way hash functions. If I hash the string red together with a random value, then if I give you the random value, you can check and say, oh yeah, that is hash of red and a random value, not hash of black and a random value. But until I give you that key, that random value, it's committed but closed. So there are lots of ways of opening this. Let's just think of this in the encryption context where this is a randomized encryption. I give you the bits of randomness, and I open these other values and show you these were all red. So again, you have good reason to believe this is red. Now in this case, this is a small case. How good your reason is, your confidence is not great. There's a 1 in 5 chance that I could have duped you in this case. So let's look at a somewhat bigger case. Maybe I could have 100 of these. And what I say is, OK, here's an interactive process. I claim that these are all red, or encryptions of red, or whatever. And you pick one and identify that. And then I open up all the others. And so all the others are red. And you think, OK, that one is probably red too. And now, since you would have had to, or if I'm proving to you, I would have had to guess in advance which of these 100 that you would pick in order to cheat you, my chance of getting away with a black card under there is really just 1 in 100, right? If I really want to cheat you, then I have to guess your random pick in advance. And I've got a 1 in 100 chance of doing that, which is better, but it's still, this goes up only linearly, and we'd like to do a lot better than this in getting high confidence. These are weak interactive proofs. Let me, question or?
you began with the title Zero Knowledge.
Yeah.
What is the thing that is, I don't have knowledge of the remaining cards.
Yes.
But now I have knowledge of the other 99.
Right.
Where are you hiding something?
Well, so the idea is that these other 99 are uninteresting in some way. They might be written. So,
How did you manage to put the only interesting data behind the card that I happen to pick?
well, it might be.
Or do I need 100 shares to find the interesting data?
No. Let me. It'll become clear later on, but let me just give sort of a preview. Suppose I want to generate, I want to produce an RSA key with some properties. And if you factor it, you can see that, oh yeah, this is the 2 primes had certain properties. Now I generate 100 things with these properties. 99 of them are going to be thrown away. The 100th you believe also has these properties, but that 100th is still protected. Okay, so that's one approach to this. But I still want to do better than this 1 in 100. What I want to do is, instead of this, where you challenge me by picking one value, and I've got a 1 in 100 chance of guessing the value in advance and hiding the right thing under there, I'm going to say what you're going to do is pick a subset of these 100 things. And I want to make it so that the only way that I can get away with cheating is if I could predict your exact subset. Now there's a 1 in 2 chance on this one, and a 1 in 2 chance on this one, and a 1 in 2 chance on this one of my guessing correctly. There are 100 things here. The chance of my guessing correctly which subset you pick is 1 in 2 to the 100. Right? Roughly 10 to the 30th. Okay, this is not going to happen. This is like, you picked a key and encrypted something, I just guessed your key. Could happen in theory, hopefully doesn't happen in practice. Otherwise, I'm not doing my job right. Okay, so if we can do this, this is much, much stronger. And there are ways. And let me give you a little bit of intuition before I show you, what this would actually look like. So the way to think of this is doing what's called a zero-knowledge proof of knowledge. And suppose what I want to do is prove to you that I can get from some starting point, it might be a graph, might be some sort of a map or some complicated structure, a maze of some sort. I can get from the start to the finish. I know a way of getting there. But I don't want to show you the way of getting there. That's the zero-knowledge part. I'm protective of this. This is valuable. What I can do, this is mostly just intuition, is pick 100 intermediate points somewhere in this large, complicated graph or structure, and wait for you to challenge. So you'll challenge by picking a random subset of these things and say you identify those. And for anything that you identify, I'll show you that I know how to get from the start to there. And everything else that you didn't pick, I'll show you that I know how to get from these intermediate points to the finish. Now, if there's any single case, any single example where I can get both from the start to a point and from that point to the finish, then I can get there. But giving you this information, I haven't shown you any path from the start to the finish. Suppose I want to cheat you. Well, since in every case you challenged me, I gave you the correct response, I showed you that I could give you the path that I was supposed to, then if I were, in even one case, able to answer the opposite way, then you know that I can get from the start to the finish. So the only way I could possibly have cheated you and not be able to get from the start to the finish is if I know exactly in advance what choices you're going to make, and then I can structure things. So yeah, here's something I know how to get to the finish from, here's something I know how to get to from the start, or I think I did this backwards, but anyway, I can get to this from the start, so I'll create a point here that I can get to from the start, I'll create a point here that I can get to the finish on, etc., and give these points. I still don't know how to get to from start to the finish, but I can convince you that I do if I guess in advance exactly what set you're going to pick. Yeah.
To convince me that you can get from the start to the finish, you have to know not only how to get from the start to the finish, but how to get from the start to every point in the set.
Oh, I picked these points. These are intermediate points that I picked. Okay. So this is intuition right now. give you a more structured form of this in a minute. But let me start off with a more direct problem that you might run into. I claim to have a private key corresponding to a known public key. So there may be a certificate of some sort that's been issued in my name, and the person with the certificate and with this private key is supposed to have access to some resources. This is a very common thing. I should be able to get into this bank account. I should be able to order some merchandise, or order some action be taken, or have access to some data, or whatever. Okay? So here's my certificate. This is showing that I should be able to get there if I have the corresponding private key. How do I show you that I have the corresponding private key? Well, one way is I can give you the corresponding private key. And you say, okay, well, yeah, I guess so. All right, good. You check it. You check that it matches the public key. It works. Great. You let me in. Not so good next time, because now you have the private key. It doesn't work so well. So here's a somewhat better method. Maybe I prove to you my ability to decrypt a message of your choice. That shows you that I really do presumably have the private key, because you encrypted with the public key. I can decrypt. You believe it. OK, except now I'm being an oracle. Maybe you've got this message that you really want to decrypt. You've been trying, you're the NSA maybe, or whoever. You've been wanting to decrypt this for a long time. And here I come along saying, OK, I'll decrypt one thing for you. Great. OK, that's not good. And you can hide this in various ways so that it's not obvious to me that I'm decrypting something that might be of value to you. So I don't want to just decrypt some message of your choice. What I want to do is something a little bit more sophisticated. I want to decrypt the message of your choice, but only after I'm sure that you already know the decryption. So it's zero knowledge for you. You will not learn anything from my decrypting this. Okay? How can I do this? Well, let's go back to this sort of graph case. I start off with this encrypted value that you gave to me. You showed me this value. You wanted me to decrypt it for you. What will happen is you will also create 100 more dummy encryptions of things that you don't care about and that I presumably don't care about. Doesn't matter. These are all your encryptions of other things. And I will challenge you. I'll pick a random subset of your dummies, your dummy encryptions, grab those, and say, OK, prove to me that you really did have decryptions of these. And you open them and say, OK, I believe it on those. What about the rest? What I'll say is, for each of the rest, you should show me that you know m times the decryption of this thing. So here's this encrypted message. Here's this. If you have both m times m2 and m2, then you have m. And you've convinced me that you're able to get the decryptions of anything that I asked you to decrypt. So if you had the decryption of this and you had this, then you do already have m. Okay? Those two things together give me that confidence of you must already have the encryption of m. You must already have m itself. So now I'm willing to give you m because you presumably already know it. And in fact, if this is a homomorphic encryption function, we could save a step and do this the other way around. What can happen is you give me encryption of m, I give you a bunch of these dummies, and I'll decrypt for you without ever opening m. I'll just prove to you that I know the decryption of this. I prove to you, you give me you have m. I prove to you that I know m without ever giving you m by I give you a bunch of these dummies, you challenge me, and I'll open things according to your challenges, and you can check that these are correct because this has a valid encryption of E of m times E of m2, which you can generate on your own if it's homomorphic. So you can save a step there, but only a quick step. But this gets at the idea. Okay? There are other kinds of zero-knowledge proofs, also very powerful, can do a lot of things, very high confidence that certain things are true. Okay. Yeah, question?
Shouldn't we use a signature to prove ownership of the private key?
Well, again, then I would be signing something. Where did it come from? If I'm signing my own, something that I chose to sign, then you might say, well, maybe I got this from somebody else who really has the key, and I just got that person to sign something last week. If I'm signing something of your choice, then I'm signing something that you've just given me, and I don't know, maybe it's a contract, a pledge to give you $1 million. So you've got that same thing of, before I sign it, I want to know that it's okay in some sense. And you want to be sure that it's not some old thing. You want it to be fresh, so you want to give it to me, but I don't want to just sign something that you gave to me. So you have exactly the same thing coming up in that case. Mm-hmm.
So I'm failing to understand the distinction between zero knowledge and zero knowledge proof of knowledge. Why isn't this called zero knowledge? Why is it called zero knowledge proof of knowledge?
Well, in this case, what I'm just proving, in this little piece, what I'm proving is I know the decryption of this value without actually revealing this value.
Okay.
Okay? It's one kind of zero knowledge proof. There are zero knowledge proofs that don't have this structure at all. I can show you that I can distinguish between things of a certain kind without giving you too much information, and prove to you that certain graph problems are solvable, graph isomorphism or graph non-isomorphism are classic cases.
Those would be called zero knowledge proof of distinguishability?
Some of them are zero knowledge proof of distinguishability. In general, it's all just zero knowledge proofs. This is just one class of zero knowledge proofs. Okay, so I've left just enough time to get back to the election example, because I really want to do this. Okay, the threshold homomorphism was able to get at the problem of who can decrypt. These zero knowledge proofs can get at the other problems that I mentioned. You can use them so that I, as a voter, can go up to a device and it can encrypt on my behalf, and I can be sure that it's encrypting the right thing. I can be sure that it's encrypted red, or whatever party that is, or whatever candidate that is, without it revealing to me the details that will allow me to go to another person and show that this other person how I voted. Also, you can use this zero knowledge process to show everybody that this really is an encryption of red or black, or 0 or 1, and not an encryption of 1,000,000. And get make sure that it's a legitimate election. So let me give you the detailed application that I've been working on. 2 sessions ago, May 2nd, I guess it was, not the last one, I ran out of this room and went directly to the airport. Went down to Travis County, Texas, where we're working on an election project. Now, Travis County, Texas is one of, I think, 249 counties in Texas. Seems like a small thing, except if you look inside Travis County, that's Austin. There are 1 million people there. It's not quite that small. There's a project that we're working on, very interesting requirements. I won't go into all the details of why we're doing it this way, but we're building one of these cryptographically verifiable election systems for Austin, and other counties are starting to get really interested for reasons I'll get into in a minute. So let me show you what the process looks like. What we've designed is a voter will go in, sign in to vote, get some sort of a token, and go up to a ballot marking device, basically a tablet. In fact, probably a Win8 tablet. With nice TPM and all sorts of nice features, but there are a lot of reasons why Win8 tablets work really well here. But basically, use this device to make selections. Nice full-featured device. You can make your choices, check them, change them. If people who have accessibility needs can go use headphones, just plug them into a USB port, whatever. There are all sorts of things that are really nice and easy to do here. This isn't voting. This is marking a ballot. So what happens when you're finished with this and you say, okay, I'm happy, I want to vote, is you get a receipt. This receipt has 3 parts. It has, actually in clear text, what's sometimes called a ballot summary. This is a list of the choices that you've made. It's not the full ballot of all the possible choices. It's just, these are the selections I made, so it's quite compact. You get the encryption, because the whole point was that we have an encrypted ballot, so here it is in a 2D barcode. And you get some sort of a take-home receipt. You could take home the entire encryption, but really anybody's going to want to deal with is just probably a hash of the encryption. Just something short, a hash code of some sort, one-way hash. Okay? What a voter can do is take this receipt, remove the take-home part, perforated. This could also come as 2 separate pieces of paper. One is the ballot summary and encryption. One is your take-home receipt. Take that off. And with this thing, haven't voted yet, you have one of 2 choices. Either you cast that ballot or you spoil that ballot. Casting that ballot means go over, drop it into a ballot box. Okay? Part of the system is every polling site has a ballot box. The voter actually casts the vote by dropping that piece of paper in the ballot box. It doesn't count if it didn't make it into the ballot box. We now have a paper record. If anybody wants to check the paper, here it is. It's in the ballot box. Scanner in the box actually reads the ballot number, so we know, yes, that ballot's in the box. Electronically, the ballot captured by the ballot marking device, that encryption can go back over the local network to the host machine and be preserved. It's not cast if it doesn't make it into the ballot box. What's the other choice? Spoil, which is go back to the poll worker and say, I'm not happy. I looked at this ballot summary. I've changed my mind. I want to vote differently. Or for whatever reason, I'm not happy. A spoiled ballot acts as a challenge in one of these interactive proofs in a sort of subtle way that doesn't have to be in voters' faces. But anybody who actively wants to gain confidence that this is an appropriate encryption can spoil a ballot or 2. Okay? A spoiled ballot means a voter takes this ballot to the poll worker, gets a new voting token, can retain the receipt, and even a copy of the spoiled ballot if desired, and go home after repeating the process as many times as desired. Anything else has not been voted. Okay? So what do we have at the end of this process? Here's the verifiable record that comes out. Here. We've got all the cast ballots in encrypted form. They're posted publicly on a public website. We've got all the spoiled ballots and their decryptions, together with any keys, any randomness necessary to decrypt them. So you, as a voter, what are you likely to do with your receipt? Probably crumble it up and throw it away. That's okay. It's okay if 99% of voters do that. Some small fraction of voters might check. Go on the website, take a look at the receipt, make sure, oh yeah, my ballot's up there. If you're really diligent and you spoiled the vote, oh yeah, my spoiled vote is up there and it decrypted the way I was expecting it to. That's the check. That's sort of this cut and choose. This, yes, it's red. It opened to the color I was expecting, to the vote I was expecting. You're probably only doing it once or twice at most, but there are a lot of voters out there. This list doesn't have to be very long to gain pretty high confidence.
How do you know that the spoiled ballot is correct?
You have...
if I brought my receipt home, I would know that what I thought should have been on there is on there.
Yes.
But everybody else's spoiled ballot,
Yeah.
I have no way of knowing if it's correct.
You're responsible for checking your own
Only
ballot
mine. Okay.
to some extent. Part of the record is this, and what will be checked by any election verifier out there is this association, and I'll get to this a little bit more in a minute, and that all of these decryptions are correct. So you don't have to check that this decryption matches. You check that this is what you're expecting, and sort of it's part of the election record that this is consistent with that according to this key. So you can imagine that election verifiers are written by the candidates, probably the candidates' parties, maybe election media. The broadcast media, special interest groups, League of Women Voters, ACLU, whatever, anybody who's interested. And it's not that hard. A professor at Rice who was part of this project assigned to his first-year programming class a task of writing election verifiers for this kind of a system. 2-week project. Most first-year programming students were able to do this. So not that bad. And you can sort of download as many election verifiers as you want, run as many as you want, or what most voters will do is believe the results. That's OK. You have your choice. You can choose who to trust here. So just quickly, how does this process work? Well, what we have is encrypted ballots. You see, you can't see what's in there. They're encrypted. OK, let's take a look. This might be what they're encryptions of. Let's make a little room. If we take these encryptions and multiply them together, we have an additively homomorphic function. So that product matches the sum, and we get exactly what we should get there. Now, that's not what's actually seen. What's seen is this. These are encrypted. But at the end of the process, the requisite number, the threshold number of election officials can come along and decrypt this aggregate value, provide the randomness so that you can check, anybody can check that this really is a correct decryption of this aggregate value that matches all of these things. Provide all this, and you've got a verified election. OK? Yep.
But I haven't verified that those casted ballots correspond to actual voters. You know, somebody,
OK.
like some malicious.
A good point. So the way that I prefer doing this is there's also a name next to each of these. This is my ballot. I can check this. And then anybody can check and see, oh, wait a minute, that person died last year.
Yes, exactly.
Or moved away or whatnot. It's preferred that this be done with actual names. There are many reasons why people are squeamish about doing it that way.
Sure.
So what we are actually doing in practice in this case is these things are associated with the take-home receipts, and there are other more traditional checks that the right number of ballots are in place. Everybody is signed in. That's what that first step was. You can get a count of the people who have signed in. You can check this against the count of the posted ballots. Everybody has the ability to actually check that their posted ballot is there. In King County, when you mail in a ballot, we have the process where you can check online and say, oh, yeah, my ballot's been received. It's been counted according to the election office. It's a claim that they've made. There's no real confidence that you have. Here, you can check and say, yep, there is my ballot. It's there. It is actually part of the count. And you get that confidence. Yeah.
Kind of similar. Is there a way for me as a voter to prove to the verifier that my ballot should have been cast, like I put it in the ballot box?
Not explicitly. The way to think of this is as an audit mechanism. You can tell if something's gone wrong. You can't necessarily correct it if it's gone wrong. You can shout and complain and wait a minute. I've got this receipt. Look at this. It's a legitimate receipt. Where is my ballot? If you're the only one doing that, then people might say, well, maybe it's a forgery of some sort. Do some forensic analysis on it. Maybe not. Whatever. If thousands of people are saying this, they've got this paper record. Something really seems to be wrong. This is going to require an investigation. But at least you know. In current systems, you've got no idea. Put the ballot in the box, go home, close your eyes. Here's the count. See you in 4 years. That's as much as you can verify. Here, at least, you can see when something's gone wrong. Okay? Yeah.
Is it possible to make each vote more secure than the aggregate sum, or does that require trusting elected collusion?
Secure in what sense? Private? Or?
Less decryptable.
With this system, no. With this system, no. And it's hard to imagine a way that it could be. Because imagine that what I do is the trustees come together, but they've just removed this last vote from the process, and they decrypt without that last vote. Then they decrypted an aggregate, but by doing that and decrypting with that vote in and without that vote in, they know what that last vote is. So in some sense, that's as decryptable as the tally if you can decrypt aggregate tallies.
So it seems like if you signed the ballot as I put it in the ballot box, then I'd have a way to prove to you that custody of my ballot.
Potentially, it turns out signatures don't help a lot here because any malicious device is going to give you a bad signature. So now, if you go home with this and you come back and say I was cheated, they'll say, well, that signature is not right. So you have to have a way of checking that signature in real time to make that a useful mitigation. Okay, please. Yep.
So the focus here seems to be to protect against fraud.
To protect against, to ensure that the tally is correct.
Right.
Okay.
And that the voter can verify that his vote was accounted for correctly.
And that all recorded votes were properly tallied.
Right. So is there a way to, so in a different country, in a different place, the voter might also need to be protected against coercion?
Yes. Oh, that's very important here. If we don't want to protect against coercion, then it's really easy. We just open this up and publish the list with the names. So this is all designed so that you have protection against coercion because you're casting your vote. In this particular scenario, it's in a monitored poll site. People are ensuring that there's nobody over your shoulder while you're having this device create a ballot on your behalf, create an encrypted ballot, and you can't decrypt that ballot. So you can't show it to a third party. You got this non-transferable zero-knowledge proof, effectively.
So if once I get rid of so for that to happen, I should leave my token behind. Is that right? Or because if I take the token out of the polling booth, then
token is the randomness. The token that I showed you at the very beginning of the process was.
I'm sorry, I meant this receipt.
No, the receipt is just the receipt of the encrypted value. The receipt doesn't allow it to be decrypted. The plain text, that stays in. There are the two things that you receive. The ballot summary, the plain text, that goes in the ballot box. If that didn't make it into the ballot box, it's not a vote. So if you took it home, that's not how you voted because you didn't vote. So you have that. Is there another? Yeah.
Yeah. So given that there's so much sort of structure here, it also seems easy to, like if I somehow squeeze in some noise into that thing, I invalidate everything in some sense, right? I mean, it's.
If you manage to get one ballot with a million
ballot,
here.
If I have a bit there, like something happens, then everybody throws up their hands in the air saying, oh, I don't know what happened, something is wrong.
Yeah, so it shouldn't happen. There's a lot here to try to keep that from happening. There should be an interactive proof that every one of these ballots is legitimate. So 1 in 2 to the 100 chance that an illegitimate ballot gets through. But there are other mechanisms. We've built in a post-election audit mechanism, and we've got that paper trail. If anybody ever cares, there's still that box of actual ballots there that people can go through. Okay.
Maybe as per that, so I mean, I could go home and just take a barcode printer and print some random noise, and it may not decrypt what I want, but it might not go well in that process. So is there also a signing component or something like that?
How would the ballot box know that it's fake? Yeah.
Right.
So the ballot box is on a local network here. So what's happening is the ballot box is communicating with the ballot marking device, and it's that okay, here's a ballot ID that's active right now. Let me know. You should probably see it within the next few minutes. Let me know when you do, and I'll record that ballot as now being a cast ballot. So that's where the process is. It's all done locally. This is not internet connected. This is a local network.
So is that where the token ties in?
The token is just the lingo here is a ballot style. You can walk into a polling site that might have thousands of different local races for different jurisdictions, and the token is just which local races are you eligible to vote for. The way they do it in Travis County is you can go into any poll site anywhere in the county from anywhere, and there may be different ballots available. So that's what that's for. Yeah.
So I want to know what sort of key material is needed, not to decrypt, but to encrypt this.
Public. It's all public key material. So the public keys of the trustees, effectively. So nothing sensitive. Yep. Yeah.
I just wanted to follow the intention of evidence here. So with cast ballots, you're showing the encrypted form, but not the actual votes. The trustees have the capability of decrypting it. They could post a decrypted list if they wanted to, or trust the trustees.
Yeah.
What is the motivation for not just posting the individual mappings between cast ballot and lists and individual votes, because the voter's name is not on there?
That can be done. There is a coercion threat called pattern voting. The idea is that I want you to vote for me as mayor. And there are these little judgeship races and county dog catcher races at the bottom of the ballot. And I want you to vote for this judge, this judge, this judge, in this particular pattern. And there are so many little races out there that I can assign you one pattern and everybody else a distinct pattern. And then I say, your vote had better show up with this pattern, had better show up for me as mayor, or you're going to lose your job. And that's the thing we're protecting.
Casting separate ballots for each race?
Yeah, effectively what happens is they get split up per race. And we do actually post the decrypted, for post-election audit purposes, we post a list of the individual votes that are cast, but they are the ballots that they're associated with are shrouded. They are encrypted or hashed, committed to. And for post-election auditing processes, we can go and pick random votes and say, here's this list that says there were 32,000 votes for this candidate. Let's pick this one and find the paper ballot that's supposed to be associated with it, and we can do that. But we don't want to have that list associated with the actual ballot numbers open, because then you can piece together the ballots and do this pattern voting trick. Okay,
Is
yes.
there a mail-in solution at all, or have to physically go there to vote?
This is designed as an in-person system. There are mail-in ways of doing similar things. Right now, what we're doing here is any remote ballot just gets remade and added to the system. You don't have an opportunity to, as an individual voter, to check that your ballot, if it's remote, has been entered properly. Eventually, we want to do that, but first pass, that's not part of the system. So 2 more slides. So why do we do this? Well, current technology, we have to trust things with current election systems. You have to trust the people that manage the election. You have no choice. If they're corrupt, you might know they're corrupt. And, hey, it's the mayor. Give me your vote. Yeah, right. The equipment and its manufacturers you have to trust. And that's a big growing problem, because often the officials just sort of bring in the equipment people and say, we don't know what's going on. You tell us what happened. And the process is used. With this method, what I'm showing you here is you can eliminate this trust. You don't have to trust anybody. Or if you don't really understand the crypto or don't want to do the check yourself, you still have the benefit because you get to choose who to trust. You choose your candidate or your party or your favorite news media or whoever else, rather than these are the people you have to trust, and if you don't like it, go take a walk. Okay? Yeah?
Don't you still need to trust the officials since they hold the decryption keys?
You trust privacy in the collective trustees of the election. So if the trustees of the election all collude, they could reveal your vote. In fact, if the ballot marking device is corrupt, it could reveal your vote because it could retain the randomness that it used in generating the encryption and then supply it to a third party. So there is trust for privacy, but the integrity of the election, the tallies being correct, is absolute. You don't have to trust anybody.
Is there any tie-in between the user's identity and everything that goes from the ballot marking device on?
In this system, no. Once you vote, then your ballot ID is retained, but your identity is not, but you do go home with a receipt that somebody could say, okay, give me the receipt. I also have all the decryption keys. I'll check all this. Yeah.
Sorry to make you answer this question again.
That's fine.
How am I sure that all of the votes are legitimate?
You mean 0-1 legitimate, or from legitimate people?
All of the votes that show up. I know that my one matches and it's all good, but how am I sure that all of the other ones correspond to legitimate votes? Again.
Well, so there are two kinds of legitimate here. Does this vote match my intentions, my chosen selections? And that's up to each voter to check. But is this vote from a legitimate voter? Yes. Is another question. My preferred way of doing that is we do have a list of names next to every vote, and then it's a matter of public record. You can just sort of check and look and see, check your neighborhood. There are people who do canvassing regularly and check the voter rolls in close elections and who's actually voted. But in lieu of that, right now, with this system where we don't have names posted, it's more traditional processes of there's a list of people who have signed in. Here are the people who voted. Here are the actual votes. The numbers match. And we get it that way. Yeah.
Just want to check trust. So the election trustees have the private key and is required to decrypt the final homomorphic tally.
Yes.
They're going to keep that secret. How do we verify the results of the homomorphic tally decrypts to the actual results?
It's a verifiable decryption. What's actually released is not just the decryption, but the randomness, the random component, so that anybody can take the public encryption function, the decryption, and the random value, and encrypt and say, yep, here's the encryption. If I take these two things, encrypt, I get that. So this is a correct decryption. Okay, last slide. Apologies for running over. Seems to be a lot of, this is good give and take. I appreciate the interest. Another benefit of this is cost. And this is where a lot of the counties, Travis County wants to do this because of good election integrity. They really seem to care about doing things right. There are a bunch of other big counties in Texas that have suddenly gotten interested in this. And basically because what they're doing is this traditional method, which is they've got this proprietary equipment that's gone through elaborate certification processes, and it's not clear the certification has much value. But there's been all this certification. It's expensive to certify. It's expensive to purchase because this is proprietary stuff, expensive to maintain. We're changing the model here. You're not certifying the election equipment anymore and then closing your eyes and hoping that it's still good. We're certifying actual elections. It doesn't matter what the equipment is. So we can use COTS. We can use off-the-shelf tablets, much cheaper. A lot of these other counties are saying, hey, yeah, cheaper, that's good. And this wasn't my intention getting involved in this, but as I mentioned earlier, when the analysis was done by people at Rice on what the best voting terminal was, they came out with, by far, Win8 tablets are the best thing for this. So, hey, great. I'm happy about that. But anyway.
Big buttons.
Big buttons. Well, large display, long battery life, peripherals, being able to do lots of USB ports. TPM is a nice thing to have, so that you can have confidence that the right code is running for privacy reasons, for other things. There are a lot of benefits to having a Win8 tablet. And also, they're cheaper than some of the alternatives. So it seems like a very good choice. Now, we're not going to make or break the company on this, but yeah, hey, it's a bonus. Okay, I've gotten to the end. Any final questions? Yes?
I have a final question. This is not, but you have a lot of experience in voting. So the previous slide, the one where you actually said, today we have to trust the officials, and cryptography allows us to overcome. Your audience are people who, science is like they don't trust in science. So that's the audience.
Absolutely.
Right. So it just feels like you're fighting a losing battle. With
so many people who said, "Well, yeah, you don't have to trust election officials, but you're asking me to trust cryptography instead. That's worse." And or even mathematics, or something like that. It's my answer to that is, at least with this model, you can choose who to trust. You're not forced to trust these people. You don't have to learn the mathematics. But you can trust, if you like Fox News, you can trust Fox News. You know, whoever. Sorry? I missed that.
I said that only works if Fox News has a mathematician. I mean, the point is, if your particular community says, well, this is a bunch of hocus pocus.
So an election verifier.
But Fox News already does that.
Yeah, it's true. A legitimate election verifier app has two possible outputs. One is, yes, this verifies. But the other is not, no, this doesn't verify. The other is, no, this doesn't verify because this step here is supposed to be A plus B and it's not. And anybody should be able to check, wait a minute, here's the point. You can't get away with saying, no, I tried it, it didn't verify, so I don't believe it. That you shouldn't buy. Yeah.
So I think you already answered this. I just want to make sure. So did you say that anybody can take all the votes published and run through the homomorphic encryption and decrypt the results and say this tally is correct?
Not anybody can do it. Only the election trustees can collectively decrypt the aggregate tally and then prove that it's correct in a way that anybody else can verify.
How do they prove it?
By releasing the associated randomness. So think of, I should have spent more time on this, I apologize. But what you can do is think of a public encryption as encrypting two values, the data and a random component. And those two together encrypt to form the ciphertext up here. Now, if I take this and decrypt it, I could just give you the data, but you have no idea whether it's correct or not. But if I also give you the randomness, then you can check yourself by re-encrypting and saying, the randomness together with the data, that does correspond to that.
So that way the officials don't have to reveal their private key?
Absolutely not. They should not ever do that. Yeah. Okay. Yes?
What do you think about voting schemes like Estonia, where they have everyone has their own certificate?
Estonia is broken. Yeah, Estonia has been very proud of their internet voting system for a few years. They got a little too loud about claiming it's great, and a couple of friends and colleagues went over, and if you look at the news just the last month, they went over and showed how easy it was to break the Estonian election system, and just before the European elections, and show that it's completely vulnerable. You can create any tally you want. It's not that hard even. And there were people in Estonia who really knew this. There were people who understood this and tried to get them to do it right and failed. So now this is very public, and of course there's a lot of embarrassment and there's a lot of distrust of these people who have come in and broken the system, but it's getting some attention. There have been people who have tried internet voting, and there have been countries that have tried internet voting. For the most part, they're not doing a good job. And there are some states that are starting to do some internet voting. We do know how to do it well. It's not being done well. Yes?
So do you see any flaws in the system? Do you see any weaknesses?
I see a lot of benefits in this system as is. There are still some issues. The biggest thing that I would like to have that's not here in what I showed you is if I see corruption, or corruption isn't the right term, but I see that I've been cheated. My ballot has not been posted, or I see that it's posted. I tried to vote for Adams, I spoiled it, and what got posted was a spoiled vote for Jefferson. So I was doing the interactive proof, you claimed all red, and I challenged you and turned over a card and it came out black. Okay, now I know there's malfeasance going on. I know there's cheating. I don't have any way to prove that to a third party, because that's indistinguishable in this system from I really did ask for a vote for black. And it gave me a vote for black in the privacy. So having evidence of malfeasance would be a useful thing to add.
When you spoil your ballot, you get to keep the label thing. Yeah.
You keep the labeled thing, but only you know who it was that you voted for. So you mean the ballot summary?
You got a sheet of paper that came out of the marking machine.
Right, right.
And it's got the name of, it's got Jefferson on it.
Yeah, it does.
There's a question of master data there. What's the master data, the encrypted data or the printed plain text?
And it could be that the encryption is actually an encryption of atoms, even though it prints Jefferson.
Oh no, right. But so the point is, if you go and you look on the website and the decryption of the barcode was atoms, but it says Jefferson on the sheet of paper, now you can go to the election officials and say, hey, why don't you guys decrypt this ballot? And you'll see it doesn't match up.
I think, you've got a good point that I hadn't realized, but I think where you have to do is you have to go to find the piece of paper in the ballot box. Because
Well, no,
that's
but it's not in the box because this was a spoiled ballot, right? So I got to take it.
Oh, right. You're right.
No, but can't you actually make a copy of a spoiled ballot and change the name?
The
of
spoiled
top?
ballot still has its plain text on it. You can prove that it doesn't match.
Yeah, it does. You're right. If you can, if there's good provenance of that piece of paper, and forensically this is legitimately printed, that's I hadn't realized that. Thank you. It's very, very useful for me. Okay, good.
And does this thwart the Google Glasses attack?
No. So there are still, this is something I've been concerned about a lot lately, and Craig knows. That basically, we've done all this work for a century and a half on this notion of what's called the Australian ballot, which is this very sophisticated process that we just take for granted, don't even realize what's going on. But the process is we vote privately in a publicly monitored environment. And that's supposed to thwart coercion. And it worked for 150 years. It was invented in the 1850s. It worked pretty well. That there are people there to watch that you're not being coerced when you fill out your ballot and you close up your ballot and you drop it in the ballot box. That doesn't work when people are wearing cameras everywhere. And it turns out there are some really serious attacks with glasses with cameras in the bridge of the nose and all sorts of things. And we've got to, there are some ways in which we might be able to deal with them, but it makes things much harder. But that's a whole other area that I'd love to deal with. And,
Coerce someone into having wearing glasses to prove that they voted the correct way?
Yeah, you could certainly, I'm your employer. I want the videotape tomorrow, or you lose your job. Yeah, and it's possible to do that very efficiently too, and large scale. I can just, I have 100 employees. I don't have to review all of them. I can review 2 or 3 of them. You're still going to do it because you might have a threat of losing your job. So anyway, okay. So one final thing before we wrap up is there is a survey, and if you want to respond, I know it's like the worst thing in the world is to give a URL that you can't click on here. But if you go to Consensus, I think all you need to do is get that, or just remember that, and we will, I think, try to mail this out to everybody whose name we have. So we've got that at least. And if you're watching remotely, okay, you have time to copy slowly, but just go to Consensus and then you can fill in the rest pretty easily. That's the most important thing.
And if you don't have access to the survey, contact Josh. And
yeah, let me know. I think I checked it, and there's an everyone box that I checked. So I think we've got that.
Is that secure?
Nope. This is purely trust them. It is supposedly anonymous, but who knows? Anyway, thank you very much.